Welcome to the ICTS Distinguished Lecture on the Universe Before the Hot Big Bang, which is going to be delivered by Professor Valery Rubakov of the Institute for Nuclear Research, Russian Academy of Sciences, Moscow. We have this series of distinguished lectures for very distinguished scientists who come around and visit us. And we are very, very happy that Valery Rubakov is here with us. And I think it's the first time a scientist from Russia actually is visiting us. So I'm especially happy about that. I would like to now invite Rohini Godbole to give a more detailed view of the contributions of Valery Rubakov. Rohini.
So now everybody can see me. Okay, so let me at outset say that it's a great pleasure here to welcome Valery to Indian Institute of Science, because as Spenta said, this is a joint exercise between Indian Institute of Science and ICTS. Actually, it's really a great honor to be introducing Valery Rubakov. I think for most of the physicists in the crowd, the tradition of Russian theoretical physics doesn't come something unknown. Each one of us has at least looked at one, or if not all, more than one, 2, 3 books in the Landau-Lifshitz series and studied from them, got scared with them. So actually Valery, I think, is a stalwart member of this very distinguished theoretical physics community from Russia. And at this particular stage, where the Large Hadron Collider and the Planck satellite data has started giving important results in high energy physics, as well as about cosmology, I think we cannot have a better speaker than Valery Rubakov here, because he is one of the experts on what we think about the theories, what might have happened in the early universe, what could have happened in the early universe. He's a great expert in that, very deep thinker, and has done very important contributions to quantum field theory. And his book on classical gauge fields has been described by some very eminent scientists, and I like that description, so I want to repeat it. The person said it's very accessible and at the same time authoritative. And I think to do both this, one requires a very special pedagogical skill. And quite apart from being a theoretical physicist who has made extremely important contributions, like the Coulomb-Rubakov effect, or giving a model about baryon asymmetry generation through electroweak baryogenesis. I could go on with listing some very technically important contributions that Professor Rubakov has made. But I think one of the most important aspect that I want to bring out is that he's one of the clearest and the most wonderful expositor of very difficult ideas that I have come across. In fact, I was telling him just before this, I still remember the talk he gave, plenary talk he gave in Singapore in the International Conference on High Energy Physics. And for particle physicists, he has been one of the popular choice when we wanted to get ourselves educated on cosmology. And here also, I think we are going to benefit. I just want to tell you that for the students amongst you, that he has written 2 very important books on introduction to the theory of early universe. So that these 2 things together should really tell you why I say that he is one of the most appropriate member to talk about particle physics and cosmology at one of the cusps of both subjects in particle physics and cosmology. I think all my practitioner friends will agree that we are really at a cusp in this subject, and I can think of nobody better than Valery Rubakov to tell you. So I don't want to stand between you and him. So here I invite him very warmly to give this lecture.
Okay.
Yeah, one moment. One moment. We want to welcome you with applause.
Okay. Thanks a lot. Thank you very much.
So,
Thank you.
this is a small memento.
Oh, thank you very much. Thanks a lot. Indeed, yeah. Thank you. Okay. Thank you for a nice introduction. Warm words. Good afternoon, ladies and gentlemen. So that's the subject of my today's talk, the universe before the hot Big Bang. Well, before that, I should say I fell in love with India. This is my first time here, and in particular with Bangalore. I think it's a great city, and it's a great pleasure to be here, both for meeting people and having conversations and all that, and also to see the country, which is a great country, of course. Anyway, so let me begin by a relatively lengthy introduction. So if most of you probably have heard of what I'm going to say, but nevertheless, this will be an introduction. So, well, let me remind you of the basic properties of our universe. Our universe is large. Its visible size is about 45 billion light years, or 15 gigaparsec. So 15, yeah, gigaparsec. So it's large. And if you think carefully about all these properties, they're very non-trivial. Why our universe is so large? The universe is old. Its lifetime is about 14 billion years. It's homogeneous on large scales, on scales exceeding roughly 200 megaparsec. The different patches of the universe look exactly the same. And that is especially clear from deep surveys of galaxies and quasars, which give us a map of the relatively large part of the universe, comparable in size, somewhat smaller, but comparable in size with the entire visible universe. So that's one piece of information which is very important, and there is a wealth of information coming from the measurement of the distances and angular positions of various galaxies and quasars. Our universe expands, space stretches out in all directions, and that is reflected by the fact that the distances between galaxies increase, and also by the fact that the wavelengths of photons also increase, in particular if a photon is emitted at a certain time t in the past, so at the distance roughly ct, and if it had a wavelength lambda, which is, you know, due to atomic processes there, so that this lambda is known once you identify emission or absorption lines, then it comes to us with a different wavelength, which is related to that one, to the original one, by what's called redshift factor, z, and 1 plus z is the coefficient here. So the the wavelength become larger simply because the space stretches out, and therefore the wavelength of a photon increases as well. Our three-dimensional space is Euclidean. This is experimental fact. In general relativity, space, even if we are talking about homogeneous and isotropic universe, space need not be Euclidean, but in fact it is. The sum of angles in a triangle equals to 150 degrees, 180 degrees, sorry, even if we are considering triangles as large as the entire visible universe. Again, this is an experimental fact, which in principle may not be the case. All of these is encoded into this in the space-time metric, which is written here. This one, very simple. X is what's called comoving coordinates, which label basically the galaxies. So you can assign to every galaxy modularly its peculiar motion around maybe a cluster of galaxies, but otherwise a certain value of x, co-moving coordinate, and the physical distances, according to this metric, vary in time. They increase as the scale factor grows. Okay? An important parameter, the important function of time, which is the relative rate of increasing of the scale factor, is the Hubble parameter. It's A dot over A. Okay? So this parameter tells you the rate of the growth of space. Now, the present value is this. It's about 67 kilometers per second per megaparsec. And in natural units, since this h has a dimension of inverse time, then its natural unit is inverse time. And in natural units, the corresponding time is 14 billion years. It's somewhat a coincidence that numerically it's equal to the age of the universe. Generically, it's not the case, but it happens in our universe, in our moment of time, that this inverse Hubble parameter equals to the age of the universe. There is Hubble law, which enables one to measure this present value of the Hubble parameter by measuring the redshift and measuring the absolute distance to the object. So this is the relationship between the redshift and distance. So that's an example of the Hubble diagram on which, on the left axis, on the vertical axis, we have, oops, we have a logarithm of the redshift, and here we have, in some units which are used by astronomers, we have logarithm of the distance. So this is a very good straight line, valid at small z, at small redshifts. All right, the key fact about the universe is that it's warm. It's filled with cosmic microwave background. The radiation, electromagnetic radiation that was emitted pretty long ago, and the universe was pretty hot at that time. But now, because of the redshift, its temperature dropped down to the value 2.7 degrees Kelvin. And in fact, the distribution of photons in energies, the spectrum of the cosmic microwave background, is ideal Planck spectrum. No deviations from black body's Planck spectrum has been observed yet, although theory predicts that there must be some deviations at small level, but there must be some deviations. They have not been seen yet. So that's probably the best black body spectrum ever created in the universe, including terrestrial, laboratory devices that are specifically used to create black body spectrum. The universe does better than that. Okay. Now it's clear that since the universe expands, its density, mass density, energy density, decreases. And if you go backwards in time, in the past, the energy density was higher. And also temperature, since it's just a redshift effect, in the past, the temperature was higher as well. Therefore, the expansion rate was also higher. The universe expanded a lot faster. This follows from what's known as Friedmann equation, the Einstein's equation of general relativity specified to homogeneous and isotropic universe, relates the Hubble parameter, expansion rate, with the energy density. The higher the energy density, the higher the Hubble parameter. That was in the past. So in the past, the universe was quite different. It was denser, it was hotter, and it expanded faster. Now, I should mention, but I'm not going to go into any detail here, that there are mysteries in the universe we don't understand from particle physics point of view. Most of it. We don't know why there is ordinary matter, why there is no antimatter. That's the baryon symmetry that Rohani mentioned in her talk. We still don't have a single theory of generation of baryon asymmetry. We don't know the origin of baryon asymmetry for sure. We are not quite confident about the role of neutrinos. Its energy density today, their energy density today is pretty small, but in the past it was higher, and they might have played some role in structure formation, probably destructive role in the structure formation. There is dark matter in the universe. We don't know what it is. There is dark energy, which we also have no idea what it is. So it's all of these, all of the composition of the universe is kind of mysterious. But I'm not going to go into any detail here. My topic is different. Let me only mention that there were several epochs, short or long epochs in the evolution of the universe, which are of direct relevance to the universe we see today and signals we receive from early universe. One is recombination, which is the transition from plasma state at high temperatures to gaseous state at lower temperatures. And while plasma is opaque to photons, photons scatter off free electrons very easily, the gas was instead transparent to photons. The density of gas at right after recombination was something like 250 atoms per cubic centimeter, pretty rare gas, and this rare gas was transparent to photons. So the photons, these cosmic microwave background photons, CMB photons, scattered last time at the epoch of recombination, which was actually a rather short epoch, fortunately, for observations. So, the cosmic microwave background photons provide us with a photographic picture. This is photons, so it's photographic picture of the universe at the epoch of recombination, which corresponds to the temperatures of almost exactly 3,000 Kelvin and the lifetime of 380,000 years. Okay, so the universe was pretty young at that time, much younger than it is today. 14 billion years is a lot longer lifetime. So the universe was younger, and still we have the picture of this universe. Here it is, this famous picture from Planck, where, of course, the average temperature, 2.7 degrees Kelvin, has been subtracted, so that the yellow and the blue point corresponds to slightly warmer and slightly cooler places in the sky. The relative fluctuation of temperature is very small. It's on the order of 10 to the minus 4 to 10 to the minus 5. And it was rather recent. Maybe for you it's already long ago, but it was in 1992 when the anisotropy of cosmic microwave background was discovered. So this is the photographic picture. It's pretty large scale, large angular scales here. So small, tiny point here, say yellow point here, is the overdense region. And this overdense region, in the end, will become a cluster of galaxies. The mechanism is simple. In principle, the places where you have an overdensity attract gravitationally matter to themselves. So this matter falls into these potential wells. The density contrast increases there, and in this way you obtain larger and larger energy contrast, mass contrast, and in the end there is collapse, and compact object like galaxy or cluster of galaxy gets formed. So even though the universe was so homogeneous, 10 to the minus, at the order of 10 to the minus 4, there's no difficulty knowing that there is dark matter. There is no difficulty to explain that there are galaxies and clusters of galaxies. Another epoch which is relevant for the thermal history is Big Bang nucleosynthesis epoch, which corresponds to temperatures exceeding billion Kelvin, or it starts roughly from 1 MeV temperature and down to 30, 20 keV temperature, and this corresponds to lifetime of 1 second to 500 seconds. So in this epoch, this is an epoch of thermonuclear reactions, which are similar to the thermonuclear reactions that, for example, happen in the sun and burn and provide energy. Here in the universe, the Q reactions produce various light elements, including deuterium, helium-3, helium-4, up to lithium-7. Okay, so why this epoch is interesting is because we can calculate, knowing general relativity, expansion of the universe, therefore, knowing nuclear physics, we know low energy nuclear physics, and also we have to know one parameter, the baryon density at that time, right? These rates of the reactions in plasma depend, of course, on how many protons and neutrons you have in your plasma, and this is essentially the only parameter that governs the result. So that's what's shown here. Here is the baryon to photon ratio that characterizes, you know, the number of photons at this temperature from Stefan Boltzmann law. So baryon to photon ratio is just a characteristic of baryon content in the universe. So this is the horizontal line, and the vertical line, abundances of various light elements, helium-4, deuterium, which is important because it depends on this parameter pretty strongly, also lithium, which is rather poorly known. But overall, the Big Bang nucleosynthesis determination of this eta, of this baryon to photon ratio, is here, and there is overall agreement between this value and the, say, helium-4. And also, which is reassuring, that there is a very good agreement with completely different method of determining the baryon content, which has to do with properties of cosmic microwave background. Cosmic microwave background anisotropy very strongly depends on this parameter, on the baryon content of the universe, and therefore measurements of the temperature anisotropy of cosmic microwave background enables one to obtain very good estimate for the baryon to photon ratio, which is shown here. It's a smaller band, but there is an agreement between completely different determinations of one and the same quantity, which means that we understand how the universe worked when it was 1 second old and when its temperature was about 1 MeV. Okay, so that's, yeah, sure, we have another epoch which is close to BBN, which is the epoch of neutrino decoupling, epoch at which neutrinos started to be free. We have some, not very direct, but some evidence, I would say rather definite evidence, that we understand how it happens. This epoch corresponds to 2 to 3 MeV temperature. There should be 2 other epochs, generation of dark matter and matter-antimatter asymmetry, but we don't know exactly when this occurred. So that's the picture. We have data since Big Bang nucleosynthesis until today by various methods. Big question marks are about generation of dark matter and generation of matter-antimatter asymmetry. But what I'm going to talk about today is this area of question marks. So after this introduction, the slogan is that with Big Bang nucleosynthesis theory and observations, we are confident of the theory of the universe of 1 second old. With Large Hadron Collider, by the way, we may be able to get to temperatures of 100 GeV, handle real measurements related to this temperature, and corresponding age is 10 to the minus 10 second. Now the question is, can we ever have a handle on the earliest epoch, which preceded the hot Big Bang? The key here is cosmological perturbations. We know that our universe is not exactly homogeneous, of course. We are an example of inhomogeneities. We people, I mean. So there are inhomogeneities. One sort of these is density perturbations. Galaxies, clusters of galaxies, stars, planets, etc. Of course, it produces the gravitational potentials. So these are observed, and we know quite a bit about their properties. That's my main emphasis of this talk. And another type of perturbations is gravitational waves. These are metric perturbations only. These are gravitational waves. They have tensorial structure in three-dimensional sense, so they're called tensor perturbations, whereas the perturbations in energy density and the associated gravitational potentials are called scalar perturbations, since they are scalar in three-dimensional sense. Now, one thing to mention is that today, of course, inhomogeneities are strong in amplitude. Their amplitude is larger than 1, and therefore we have to deal with nonlinear theory. Whereas in the past, their amplitudes were similar to the temperature fluctuation over the sky, so their amplitudes were about on the order of 10 to the minus 4 to 10 to the minus 5. And that makes life easier a lot, because we can use linear analysis, linear field equations, linear hydrodynamic equations, etc., to study the properties of these perturbations theoretically. There is wealth of data. Cosmic microwave background, I will speak about it a little later also. But cosmic microwave background gives us a lot of data on both temperature and isotropy and polarization. By the way, polarization is interesting in particular for searching for gravitational waves, and most of you have heard about BICEP 2 story, which started, to me at least, maybe to somebody else earlier, but for me, most of us, it started in March this year, and it kind of degraded in September, by September. So, okay, anyhow, we have also deep surveys of galaxies and quasars. We know the map of the universe. We can construct various correlation functions, etc. So this gives us, again, measures of data on cosmological perturbations. There is gravitational lensing techniques, etc. So all in all, they are in good agreement with each other. So the different methods are shown in different colors. Green is cosmic microwave background. Black is galaxies and quasars, weak lensing, etc. They are on one and the same smooth curve. And this smooth curve shows the dependence of the power, or power spectrum, on the wave number, inverse of the wavelength. To understand what's shown here is that one notices that density perturbations actually make a random field. So K is wave number. In the linear regime, you can safely talk about wave number, about the Fourier decomposition. So this is wave number. And this is the power spectrum of this random field transferred to the present epoch by using linear theory, which is not the case in real universe, but you can play this game to normalize the various data in one and the same way. So there is very good consistency here, and this means that, again, we understand the behavior of now perturbed universe reasonably well. Now, from this, we have learned a lot of things, and one fundamental thing in particular. Namely, we learned that the old picture of hot Big Bang is wrong. Hot Big Bang means that you start off with singularity in the past, and immediately hot universe begins, just from singularity, or near the singularity. Of course, singularity itself is not something physical, but the old picture was that there was something unclear, but then once you get into more semi-classical regime of general relativity, then you have hot universe, and it expanded and become the universe we are now in. But that's not the whole story. That we know from the study of density perturbations. That's the main message of this talk. We know it's not a matter of belief or, religion or anything. It's knowledge. The key point here is causality. Let's come back to this Friedman, Lemaitre, Robertson-Walker metric, and let me consider early epoch in the evolution of the universe, which is called radiation domination. Never mind, this is an epoch that existed before the temperature was around 1 electron volt and lifetime 50,000 years. So it's somewhat before recombination. Then, at that time, the scale factor grew like square root of time. That's the solution to the Friedman equation. And what we would like to compare it with is the cosmological horizon. So if we are in the hot Big Bang picture, suppose we are, then there is a beginning of the universe, the moment of the Big Bang. And suppose you emit signals at the Big Bang epoch, at Big Bang moment, which travel with the speed of light, the largest speed we have. Then they will travel finite distance, and this distance, in this particular case, will be 2 times ct, where c is the speed of light. It's slightly larger than ct, simply because not only photons run away, but also the universe expands. But in any case, the visible size of the universe at time t is a quarter of t, or ct. Right. Now, the wavelength of a perturbation of a given perturbation, I'm in Fourier space, so I can consider perturbation of a given wave vector. Given perturbation has a certain wavelength, and this wavelength increases like scale factor, right? The universe stretches out, the wavelength increases accordingly, and therefore, in this regime, radiation domination, the wavelength increases like a square root of time. And this should be compared to the behavior of the horizon. Now, at early times, it's clear that when t is small, then lambda is greater than the horizon size. So the perturbation was huge compared to the universe visible at that time. But then, as time goes on, another regime, which is more convenient, more conventional, takes place when the wavelength is smaller than the horizon size. And that's the perturbations we are interested in. Perturbations corresponding to galaxies have kind of galactic size. Perturbations corresponding to the clusters of galaxies have the size roughly of the order of the size of the clusters of galaxies, and all of these are much less than the size of the visible universe. So today we are in subhorizon regime, but in the past, every wavelength was in subhorizon regime. Every interesting wavelength entered the horizon, this change of regimes occurred after the nucleosynthesis epoch, so there is no guesswork. We know that happened. We know how the universe expanded at that time. So, but you can immediately say, wait a second, how could that happen? That the wavelength of perturbation was larger than the size of visible universe, the size of a causally connected region in the universe, right? So this is the causal structure of our universe in the hot Big Bang theory. We have a singularity here, we have horizon, light cones, okay, we have a certain size of a horizon, and what we see today is in fact many horizons. And this is the time of recombination, for example, at which we have photographic picture of the universe. The angular size you calculate at recombination has angular size of the horizon at recombination is about 2 degrees today. So this size in degrees is about 2 degrees. So if you look at different places in the universe separated by more than 2 degrees, then you see the regions which in this picture never talk to each other, right? This is known as horizon problem. There are about 100,000 regions in our visible universe that did not talk to each other by the recombination epoch. And yet, they are exactly the same. So how come? Well, that might sound as a rather vague question, how come? But it is a lot more sharp if you consider properties of recombinations. So the issue is, what is the origin of the perturbations, right? And there are, in principle, 2 possible answers. One is that they have the Big Bang theory, hot Big Bang theory is correct. There was a singularity, and immediately after the singularity started the hot epoch. And then one has to conclude that perturbations were never superhorizon. They have been generated at the hot epoch, but when generated, they were smaller already. Their size was smaller than the horizon size. That's not impossible. And in fact, in the mid-90s, or beginning of 90s, there was quite an activity of trying to propose models of this sort, and some of them were successful. For example, you can have cosmic string, the closed cosmic string, a compact object of very high mass that will attract matter on it, and in this way seed the density perturbation, right? Then somehow they disappear, they annihilate with themselves, and the overdensity in this place remains, and this is the density perturbation for a galaxy, or cluster of galaxies. That's worked pretty well, actually. And this kind of construction is the only possibility if you believe the hot Big Bang theory. But now we know that this is not true. We know this is not true. To understand that, in fact, once you understand all this causal structure, you immediately see from this picture that this is not true. By your eyes. You look at this picture, you see that there are perturbations whose size is definitely bigger than 2 degrees, right? This underdense region, low temperature region, is a lot bigger than 2 degrees. Or this overdense region, here, 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 it's certainly larger than 2 degrees. So you have perturbations of all scales, including the scale which is greater at recombination, including the scale which is greater than the horizon size at that time. So they could not possibly be generated at the hot epoch, right? Because they were always bigger than the causally connected region in the universe. They could not be created in a causal way, and well, you may give up causality, but that's probably too much.
So if it was not the case, you would have only seen the scale of the defect.
Yeah, you will see the angular scale at most 2 degrees. So this picture will be at most 2 degrees. Perturbations and nothing of bigger size. For shorter wavelength, the story is the same. They also could not have been generated in the hot epoch. And the reason is this. Suppose that the solution, let's assume that there was super horizon. Let's assume that there was an epoch preceding the hot cosmological epoch. Let's see what will be the prediction for coming just from this assumption, and see if this prediction is correct or not. So we assume that the hot epoch was not the first one. We assume that the perturbations were generated at earlier epoch, and they were super horizon at the radiation domination epoch in the hot stage. Okay? So they were at super horizon regime, and we have to solve the wave equation for density perturbation, say, in baryon photon component. Because the universe expands fast, the solutions to the wave equations are not the standard solutions. There are two solutions, as always. There are two solutions to the second order differential equation, and one is a constant in time, this constant mode, and another is the mode that goes like inverse power of time. Okay? This is under assumption that the modes were super horizon. Now, this second solution, if its amplitude was reasonable, not very large early on, it would decay by the horizon crossing since time goes on and the solution decays. Or conversely, if you think that at the horizon crossing, when the regimes of evolution change, if you assume that this perturbation, this part of perturbation was sizable, then early on, at very early epoch, this was a huge perturbation in the energy density, right? So our homogeneous and isotropic background is now inconsistent. We have to start from scratch and study a theory of a universe which is originally very anisotropic and inhomogeneous. And we will get to completely different picture and completely different predictions. So the consistency of the whole picture tells you that this term must be absent before the mode becomes subhorizon. So in the regime later regime, when the mode is subhorizon, when the size of the wavelength is smaller than the horizon size, this is conventional behavior, like, I'm talking, so the waves coming from my mouth do not know anything about the expansion of the universe, right? So that's subhorizon modes. And these subhorizon modes just oscillate. But these oscillations start with very particular initial condition. Then density contrast is non-zero, but the velocity of medium is non-zero, is zero, right? In other words, the time derivative of the velocity of density contrast is zero. Okay? So in the plasma, the perturbations are acoustic oscillations in the subhorizon regime. But these acoustic oscillations start off with zero velocity. And this means that the oscillations have very definite phase, right? You have this particular initial condition. If you then solve your wave equation with these initial conditions, what you get cosine, right? In principle, you get combination of cosine and sine, or in other words, you might have some phase here, but this is not the case. But this is not the case. So, the cosine is cosine, no phase, because of the initial condition. So the very assumption that the modes were created early on, before the hot Big Bang, tells you that there must be oscillatory behavior of your density perturbations in time, and by the recombination time, you get some factor here, which is an oscillatory factor of the co-moving momentum, k, or wavelength at that time, right? So you get oscillations in the momentum space, or wavelength, right? And this is remarkable because it immediately translates into the picture. You, of course, have seen it, but it immediately translates into the picture of CMB temperature angular spectrum. What one does there is that one measures the temperature at different positions in the sky, makes Fourier decomposition over spherical harmonics, and measures the value of these coefficients, okay? And this is called temperature angular spectrum. One averages over m's over second quantum number. But the point is that for the larger the multiple number, the smaller the angular scale. That's the usual story about the Fourier decomposition. So, and therefore, if you have this oscillatory behavior as a function of k, this means that different waves come to recombination epoch at different times. Different wavelengths are seen at different angles today, and therefore you expect oscillations as a function of angular size or as a function of L. And that's precisely this famous figure, which you have seen many times probably, which shows you the temperature angular spectrum as a function of, say, multiple number or angular scale. That's the same thing. Okay? So here is this picture. These are the oscillations. So, for example, this first peak corresponds to the waves that become just for which this argument of cosine just becomes equal to pi, right? The angular scale is around 1 degree, not 2 degrees, simply because the speed of light is not equal to, the speed of sound, sorry, in the plasma is not equal to 1, right? That's a reflection of the fact that the speed of light is not, speed of sound is not equal to 1, etc. These deeps correspond to, the first deep correspond to the wavelength that, this is angular scale of wavelengths for which this cosine is equal to, what is it? Pi plus pi over 2, 3 pi over 2, okay? And this cosine vanishes, etc. So all these oscillations are exactly coming from the oscillations in the momentum space. And this immediately tells us that indeed our initial conditions corresponded to the wave, to the perturbations that have been created before the hot Big Bang, and at the hot Big Bang epoch, initially they were superhorizon. So that's the proof of that. On the other hand, if you try to make your perturbations in a causal manner during the hot stage, you don't have this. You don't have any reason for the phase to be fixed, and therefore you have no reason for the oscillations to occur, and that's precisely what happens in models which involve, for example, strings, right? So here is the prediction from the model involving cosmic strings as seeds for topological, for density perturbations, and there is nothing like oscillatory pattern we have in experiment. So all this tells us that indeed all the perturbations we see have been generated at epoch that preceded the hot Big Bang. So we know that now that the hot Big Bang epoch was not the first one. There was a previous epoch which was quite different. It was different in the sense that in terms of conformal time, this is not conventional time, that's what's called conformal time, another time variable in which the light travels like in Minkowski space. So this is indeed light cones. In this time coordinate, the beginning of the universe should be much, much early than in the hot Big Bang theory, so that our entire visible universe is within the light cone emanating from possible beginning. Okay. Now the question is what it is. What is this epoch? So we are sure that there is one, but now the second question is what it is. Well, the best guess is inflation, which is a cosmological expansion with nearly constant Hubble parameter, meaning that the scale factor exponentially increases in time. And exponent is a very strong thing, right? I shouldn't tell you the story about Raja and chessboard, and that's what happened in the inflationary universe. In only 100 Hubble times, the universe expanded from Planck size region, 10 to the minus 33 centimeter, out to almost the entire visible universe. You need only 100 Hubble times to do that. That's the chessboard. Now, for us, it means that perturbations were sub-horizon early at inflation, and as the scale factor increases exponentially and Hubble parameter stays nearly constant, these small perturbations eventually become super-horizon at inflationary stage. Right? So the situation is the opposite. You start off with sub-horizon perturbations, they become super-horizon, and they remain super-horizon until fairly recently when they again enter the horizon at the relatively recent epoch. Now, another point I would like you to take with you is that inflation is not a theorem yet. There are competitors, there are alternatives, which, for example, there is an old idea that the universe might have started from the contracting stage, that there was a contraction, the stage which is kind of opposite to what we have today, then bounds, meaning that the contraction terminates and the expansion begins, and then the hot Big Bang epoch starts. In this picture, what you want to do is to generate perturbations at the contracting stage, right? Another possibility, which by the Italian guys who suggested it is called genesis, very brave name. But anyhow, the idea is that the universe could actually have started from nearly empty and flat stage when the energy density was very small and space was essentially Minkowskian. And then, by a miracle, energy density in the universe increased, and according to the Friedmann equation, the expansion rate started to increase as well, so the universe speeded up its expansion, it becomes denser and denser, and then at some point the energy density of something that drives this genesis stage should get transformed into heat. This is difficult, and until recently it was thought that it was not impossible. It was impossible. The reason is that one of the Einstein's equations in the expanding universe has this form. It relates the time derivative of the Hubble parameter to a particular combination, P plus rho, where P is effective pressure, special component of energy momentum tensor, and rho is energy density. Now, you need this, if this, you consider one of these scenarios, you need this time derivative positive. You want to have negative Hubble parameter initially, and then positive in the bouncing universe, or H is equal to 0 initially and positive later on in the genesis scenario. So you need at the initial stage that this, at some stage, that this time derivative is positive. But positivity means that effective pressure must be less than minus energy density, and energy density should be positive. This relation here, pressure less than negative energy density, is rather difficult to achieve. Typically, if you do this in a simple manner, you get into troubles, you get into instabilities, like ghosts or other types of instabilities. But relatively recently, it became clear that you can have special fields. You need special fields to design, like you need inflaton in the inflationary cosmology to drive inflation. You need special field to drive bounce or genesis. But there are fields which are called Galilean fields in general, it's kind of generic name for them, which can have this property that pressure is less than minus energy density, and at the same time, no obvious pathologies. So it is difficult, but by now it appears that it's not impossible to have these scenarios in a self-consistent way. Now, there are other suggestive observational facts about density perturbations. One is Gaussianity. For a field theorist, Gaussianity means Wick theorem. The Wick theorem is the same thing as Gaussianity, technically. But once we hear the word Wick theorem relates multiple Green's functions to a two-point function. Okay? That's the Gaussianity. So Gaussianity of primordial perturbations, the random field of primordial perturbations, immediately suggests that their origin is vacuum fluctuations of some fields. These fields are to be weakly interacting, because Wick theorem applies to non-interacting fields. Also, initially they have to be in their vacuum state, because again, Wick theorem applies to vacuum state only. It's valid for vacuum correlation functions of quantum fields. So the fact that there is Gaussianity there means that it's very likely that we are dealing with that the origin of perturbations is vacuum fluctuations of some fields. Which fields is a different story, but these are vacuum fluctuations of some fields which eventually got enhanced and became perturbations in energy density. And every single suggestion of generation of density perturbations nowadays operates with the idea that original vacuum fluctuations get enhanced in one and the same way. So it's very likely that all of us are children of vacuum fluctuations, right? So our remote relative is lamp shift. Okay, so inflation does the job very well. Vacuum fluctuations of every light field get enhanced because of the rapid exponential expansion of the universe. So do the inflaton perturbations, and in the end, the perturbations in the field that drives inflation, the photon, give rise to perturbations in energy density. That's the simplest picture in inflationary theory. So indeed, there, the vacuum fluctuations of a certain field, in the inflationary case, inflaton, are the origin of perturbations in the universe. Similar mechanism works also in alternative scenarios, but there it's less automatic. But still you can have, you don't care, maybe the universe needs not anything to do anything automatically. Maybe there is some mechanisms that do the job. Now another thing is that primordial power spectrum is almost flat. Flatness means that power spectrum with appropriate normalization is independent of momentum. The normalization is such that this P of k power spectrum contributes to the fluctuation in the energy density in the logarithmic interval of momentum. So flat spectrum means that every logarithmic interval of momenta contributes equally into the fluctuation of your field, of your density field. Now the conventional parameterization is the momentum to the power ns minus 1 for historical reasons, and ns equal to 1 corresponds to flat spectrum. Experimentally, the spectrum is indeed nearly flat. This scalar spectral index is indeed close to 1. It's 0.96, even though it's now known that it's not equal to 1 exactly. Now, the third point is that there must be some symmetry. Flatness of the spectrum cannot be just a random property. There must be some symmetry that guarantees that the spectrum is flat. Well, in inflationary theory, you have the symmetry of the Sitter spacetime, of the symmetry of this metric, which in particular involves scaling dilatations of spatial coordinates together with shift in time, so that there is no scale and therefore no preferred length scale, which might be interesting twist in all the discussions. And there are indeed toy models and general arguments showing that the conformal symmetry may be indeed responsible for flatness of the spectrum. The point here is that conformal group involves dilatations, and again, you don't have specific scale, length scale in your problem. Now let me skip this. This has to do with the general setting where you indeed get flat spectrum of perturbations, but let me skip that. Let me come to the last part. Can one tell? Are we able to get handle on the real situation in the universe? Well, to tell between the different, to discriminate between different options, one again has to study perturbations. That's probably the only possibility. But one has to find more intricate properties of cosmological perturbations. Primordial gravitational waves is one of these properties because they are predicted by inflation only. No alternative predicts it. The reason is that inflation enhances all perturbations of all vacuum, of all fields, including gravitational field itself. So perturbations of gravitational field in vacuum in the end result in primordial gravity waves, which are predicted to have sizable amplitudes, and relevant gravity waves have huge wavelengths, starting from about 100 megaparsec. They can make detectable imprint on anisotropy as cosmic microwave background and polarization. This would be a smoking gun for inflation. Okay, so that's the situation today. The amplitude of gravity waves normalized to the amplitude of density perturbation squared is now bounded by about 0.15. No gravity waves have been discovered. There was a claim of BICEP 2 that this ratio is about 0.2, but that's probably not the signal from primordial gravity waves, but rather it is due to emission from our galaxy. It's not of cosmological origin. So gravity waves have not yet been discovered, but it would be extremely interesting if they are. Non-Gaussianity means, in particular, for example, that the three-point correlation function doesn't vanish. If for the Gaussian random field it vanishes. So non-Gaussianity would be very interesting to observe. There are rather strong limits coming from Planck on non-Gaussianity, but still many models are consistent with these limits. Observation of non-Gaussianity and measurement of non-Gaussianity will give you a lot of information because this three-point function is a non-trivial function of all the invariants, and therefore, looking at the shape, you can tell what is responsible for this non-Gaussianity, what kind of interactions are responsible for this non-Gaussianity. In the simplest inflationary models, it's very, very small. It's essentially unobservable. Once non-Gaussianity is found, then it's not the simplest version of inflation, at least. And in fact, different models, including alternatives to inflation, predict very different functions g here, and therefore one can possibly discriminate between various scenarios by measuring non-Gaussianity. Another possibility is that the universe at the pre-hot epoch was not exactly isotropic. That's also a possibility. You can design models of this sort, and in fact, it is quite natural in conformal models that you get effective anisotropy in our part of the universe. And that would translate into the dependence of the power spectrum on the directionality of momentum. For example, like this. That would be very interesting. Again, there are limits coming from Planck, or people who use Planck data, rather, to search for statistical anisotropy. For the time being, again, there are only limits. So let me summarize. Summary is that first message is that we know that the good old hot Big Bang epoch was not the first one in the history of the universe. Second is that inflation is consistent with all data, and in fact it predicted most of the known properties of perturbations before they were measured. That's its strength. But this is not a theorem that the world started from inflation. There are competitors, and in particular interesting for me competitor is a conformal scenario in which the universe begins from unstable conformal stage. There are others. There are many options which I partially listed here. So that's the second message. The third message is that we now know only very basic things about the cosmological perturbations. And we badly need to measure more intricate things. We need to discover less trivial properties of cosmological perturbations, like primordial tensor modes, gravitational waves, non-Gaussianity, non-trivial correlation properties of density perturbations, or statistical anisotropy. So the final slide is that in cosmology, as well as in particle physics, we are at the eve of new physics, right? With the LHC, we still hope to get a signal from new physics. The next run with nominal energy will be crucial in this regard. On the cosmological side, we have plenty of data coming from Planck, from future and present dedicated polarization experiments. A lot to be learned from the data, new data, and better theoretical understanding of the structure formation. So it's in principle a very powerful tool to study the properties of cosmological perturbations. So we have a chance to learn what preceded the hot Big Bang epoch, what was the new cosmological physics. But it's not guaranteed, right? Both in the case of LHC, we are eager to have signal from new physics, but nature may not be so kind to us. Likewise, in the cosmological case, nature may not be that kind to provide us with information about the start of the universe. We are not, who knows how it works. So there's no guarantee, but I'm still optimistic. I think we will learn both new physics at particle physics, in particle physics domain, and also in cosmological domain. Thank you. I don't know where. Here.
So you
Yeah, sure, of course.
Okay. So thank you very much for this detailed talk. So questions? Yeah?
Universe.
Yeah.
I would like to know one thing. It's associated with contraction and then expansion, and it has to be done within a particular volume. I mean,
no.
The way I can see. I'm not an expert in these things. I'm just trying to understand generally. So what do you think? What may cause this contraction and what may cause this expansion?
One thing for non-experts is that you should not think of our universe as a, ball with matter that today expands, and this bouncing, contracting, bouncing universe first shrinks and then expands. It's not a ball of matter. The entire space is homogeneous and isotropic, as far as we can tell now. So we are not embedded into some, likewise, our three-dimensional space is not embedded into higher dimensional space. It's just as it is, okay? So the question is, how could that be that the space shrinks, the entire big space shrinks homogeneously to some approximation, and then starts to expand again. For that, you need to have certain matter that has a property that in the beginning it works more or less like conventional matter, so that the universe contracts, but then it should have pretty strong pressure, negative and strong, to prevent this contraction and let the universe expand. That's the answer.
Then after expansion, again there will be contraction?
Well, that we don't know. There are pulsating models saying that far in the future, our universe stops its expansion and becomes contracting again. There are pulsating models, but we don't know. I mean, it might be that the future of the universe is that it stops expanding and collapses back. So this pulsating picture, it makes sense, but it also makes sense to consider the universe that collapses and then expands once.
Yeah.
In your conformal models, do you have to break the conformal symmetry, right?
That's right.
How do you plan to break it?
Well, it's a good question. As I told you, what we deal with, what is done until now, there is no complete scenario. What is done by now is to consider conformal stage itself, which is by itself not entirely trivial thing. But there is a question which you asked, that the conformal symmetry must be broken one or another way. I mean, there are toy models how to do that, but nothing more than toy models. And second, you also need the energy density. So conformal models always include some field that rolls away from conformally invariant state. So this field, or effective field, rolls away, and during this rolling you generate perturbations. Now, you have to stop this rolling, that corresponds to breaking of conformal invariance, and also you have to transmit its energy into heat, which is again not a trivial story. Again, there are toy models of how to do that, but nothing more than toy models. it's relatively recent development. It's not, what is it, 35 years old. Like inflation, maybe 5 years old, but not more. So we're learning. But by having a conformal mechanism, you on the symmetry grounds only, you can actually predict a lot of things. In particular, shape of non-Gaussianity in some limits, or statistical anisotropy. And that's just model independent properties.
Are there any other questions? Then I had a question actually. Is when we have this alternates to inflation that you talked about, but all these models still will, I always used to think that when you see the power spectrum and the dips and the peaks,
yes.
I used to take in my mind that as the proof that it's really proof for inflation.
No, it's a proof.
So that's,
no. Many people have this in mind, but that was one of my points.
Yeah.
That these peaks only tell you that perturbations were generated before the hot stage. What was this hot stage? These peaks themselves don't tell you. They tell you that their origin is before the hot epoch. That's all. Whether this was inflation, conformal, beginning, or other scenarios I described.
So this more accurate measurements is the only way to...
Yeah, you have to figure out, power spectrum is not enough. You have to figure out either non-Gaussianity or the gravitational waves.
So somewhere some tensor structure.
Tensor perturbations, yes.
Yeah,
so that's what you need.
And the other question I had maybe for the sort of as a is that what can the LHC do in the coagulant plasma formation from the multiplicity analysis of multiplicity distributions or something? There have been ideas of trying to do some kind of CMBR type analysis in the multiplicity.
Well, I'm not expert in that.
Yeah,
so I'm not an expert in that. I don't know, but I think, it makes sense to make a,
because that's more or less a similar initial condition.
Yeah, it makes sense to make a Fourier decomposition of your, if it's possible, of your signal to see, this kind of peaks maybe of different origin, but some features in the Fourier modes.
So that would be really like trying to see the Big Bang in that LHC, right?
Not exactly, but some features in this Fourier space may tell you some stories about quark-gluon plasma. But I'm not an expert in that. The very idea sounds reasonable.
Okay, so I don't see any more questions. So let me thank, and I hope you all join me.
Thank you.
Rubakov for really an excellent talk. And then all of us can move over to the room across and have a cup of tea.